Richard Gore from University of Cambridge. He will also talk about instrumental inequalities.
Let me say that I don't feel like I have much else to say after Ismail's wonderful talk, but I'll still try. And I guess I'll just try to convey one message that CHSH inequalities and stuff like that do show up when we consider partial identification in statistical econometrics. And for that case, especially when that involves certain variables, we would want to use those inequalities to get the tightest bound as possible for partial identification. This is joint work as part of my PhD thesis done with Thomas Richardson. Okay, so let's start with our usual graph. So for now, just think about a really ideal case where we have Z being completely randomized, okay? So think about the encouragement design. And for this talk, I will going to assume that the instrument, the treatment, and the outcome Y, all of them are going to be binary. And here is a case. For example, when you walk into a clinic and the doctor secretly draws a coin from his drawer and just see, you know, whether he or she wants to give you encouragement to get vaccine. And that's the instrument Z, 0 being encouraged, not encouraged, 1 being encouraged. And X is the treatment with whether you do go to get the vaccine, and Y is the outcome, whether you get infected or not. And I'm going to use the notation Y of XC to denote the counterfactual outcome had you taken the specific encouragement status and specific treatment. And the goal of this talk would be not about the type of inequalities for falsifying the instrumental variable assumptions, but rather I will focus on how to get the sharp bounds on the average treatment effect. So that is the difference in expected value of those potential outcomes when you flip the status of the treatment X. I want to say that Y indexed by XZ, the first coordinate, is the treatment we care about. We want to get this bound expressed as the functionals of this observed distribution Pxyz. Okay. So in this case, we may make the following assumptions. The first assumption is an exclusion restriction that basically says on the individual level, encouragement would have no effect. Means encouragement only has effect through the actual vaccine that you're taking. So that means on the individual level, the random variable Y keeping the same X while flipping Z would be the same. And that means essentially this potential outcome random variable Y of XZ is only indexed by X and is not a function of Z. Okay. The other assumption that would be plausible in this case is the joint exogeneity that basically says because the instrument Z is completely randomized, you should find plausible to be jointly independent with the vector of the potential outcomes of Y, and there are 4 of them. Well, in the individual level exclusion, I can write Y of X. So there are only 2 actual potential outcomes. And the joint exogeneity can be written as Z independent of this vector, Y of X0 and Y of X1. Oh, okay. So this is the potential outcome notation. Y of XZ denotes the underlying potential outcome of whether you're infected had you receive a particular treatment X, a particular encouragement Z. So it's a counterfactual variable. That is the goal of our inference, right?
No, sorry, I missed that part when you define Y of X.
Right. Exactly. So do interrupt me anytime you find it. Good. So under these 2 assumptions, the individual level exclusion and the joint exogeneity, by joint I mean Z independent of this random vector. The Balke and Pearl worked out the following bounds on the average treatment effect, and they further proved that they are sharp under these two assumptions. So here is the bound on the average treatment effect, and tau is average treatment effect we care about. And both the lower and upper bound is a, well, the lower bound is supremum over 4 linear quantities of the observed distribution, 8 observed distribution, and the upper bound is minimum over 8 linear quantities of the observed distribution. You don't have to look too closely, just remember 8 and 8, okay? All right, but there could be concerns about applying those Balke-Pearl bounds for partial identification, because the assumptions we previously have are actually cross-world. What that means is that it involves stating something about the two counterfactuals that you can not see simultaneously, even hypothetically. So that means, more precisely, if we imagine a hypothetical study where both the encouragement and the actual vaccine status are randomized, and this is the 4-arm study, both X and Z are randomized, and based on the data from that hypothetical study, we wouldn't be able to reject the hypothesis of the individual level exclusion and the joint exogeneity. Further, about this joint exogeneity, this assumption may become less plausible when Z is not randomized, which is the case for many actual Z we use for example, in econometrics. For example, Z being the state laws or proximity to the college, you might just think, this is not randomized, so you might be a little bit concerned when you postulating this cross-world assumption of joint exogeneity. I would want to say that, so is that clear that these are cross-world unfalsifiable assumptions? Because even in a hypothetical randomized study, if you look at a person, right, you would only see Y of a single X, single Z, you wouldn't see the other guy, so that you wouldn't be able to actually compare the two potential outcomes to see if they are equal. And for the next one, for each unit, you only see one of the Y of X, Z's, you wouldn't see the others, so you wouldn't have data to reject the hypothesis of this joint independence. Okay. I want to say that the Balke-Pearl bounds can be derived under weakened, but still cross-world assumptions. Okay, so let's switch our assumptions to some weaker assumptions. So we can replace the individual level exclusion with the population level exclusion. That's what I call the marginal stochastic exclusion. So instead of saying the two random variables on the individual level are the same, I'm only saying that for fixed X, when I flip Z, the individual level, the random variable would have the same distribution. Because we're dealing with binary data, the binary potential outcomes, so this is equivalent to say the two have the same expectation. And this is assumption which can be potentially falsified in an experiment where we randomize both X and Z, because you can look at the two arms for a particular X, you can look at the two arms for that X of different Z and compare their actual mean. And if you find the means to be different, then you should hypothetically rule out this hypothesis. For exogeneity, I'm going to replace joint exogeneity, where Z independent of 4 potential outcomes, by this margin exogeneity, the basic saying Z independent every one of the entry of the joint of the random vector. And this is assumption where you can also have a hope to falsify in a hypothetical experiment, because you can look at arms data, arms Y, and see if that's independent of Z. So those are the weaker, more plausible assumptions that have a chance to be falsified by a hypothetical experiment. Now, under these assumptions, Manski and Robins derive the bound on the average treatment effect. And this is a bound where I have the maximum over 4 numbers in the lower bound and the minimum 4 numbers in the upper bound. So actually, if you compare this Robins-Manski bound, so this is a weaker bound compared to the Balke-Pearl bounds. You see actually the Robins-Manski bounds upper bound, lower bound is only taking the maximum over a subset of those numbers, and the upper bound is only taking the minimum over the subset of the numbers, and hence the Robins-Manski bound would be a weaker bound than the previous Balke-Pearl bounds. So these Manski and Robins bound are also called the natural bounds. So the Balke-Pearl bounds are strictly sharper than the Robins-Manski bounds. So the question of this talk is to see whether we can fill this gap or is this gap fundamental in some sense. Okay, so for the rest of the talk, I'm going to use counterfactual of S as indexed by Z. Just to think X is actually an effect of Z. And this is just to align with some of the literature, and this is not essential for our derivation. So previously we have this graph. Now if I imagine Z could have effect on X, so I'm going to use this graph where I allow the latent confounding between Z and X, but this confounder should be independent of the confounder that confounds X and Y. Okay, so I'm going to try to formulate the previous weaker hypothesis, that is the marginal the marginal exclusion, the stochastic exclusion, and the marginal exogeneity in terms of the latent variables. So what I'm going to do is to use this single world intervention graph, SWIG, introduced by Thomas and Jamie. So I'm going to look at this graph, and I'm going to draw the single world intervention graph. So what that means is Z and X are variables that can be intervened. So I'm going to intervene at Z. And that Z splits into 2 parts, the random part Z and this fixed part little z. And I'm going to index the counterfactuals of x, y by the value of the little z. And then I'm going to, yes?
Just as a clarifying issue, so this is a single world intervention graph, right? But there is a missing edge from Z to Y here. And earlier you said that the fact that that edge is missing corresponds to a multi-world statement. I just wanted to flag that. It's an interesting thing. I don't think there is a problem. That's just a feature of SWIGs. That's a little factor.
Oh, yeah. So I'm not sure I'm following.
So you were talking about exclusion restrictions, right? So
right.
Missing edge in this way corresponds to exclusion restrictions. Exclusion restrictions are individual level multi-world statements, as you said a few slides ago, right?
Right.
I just think that's interesting to point out, basically.
Right. I so see. So that actually means the exclusion restriction on the stochastic marginal level.
Yeah, you can do that.
Yeah, it's a latent variable. Yeah, this is precisely what it says. It's a latent variable stochastic exclusion of the reformulation of the exclusion. Okay, so now you can read this graph that 2 assumptions would replace our 2 previous assumptions. So one, the fact that, as Ilya said, there's no edge from z to y. This missing edge from this fixed z to this counterfactual y signifies the latent variable stochastic exclusion. What that means is that this y of xz essentially is only indexed by x on the population level. Furthermore, well, graphically, you will read this as z, not connected to y of xz given u. So this is the statement that the counterfactuals with different z's conditional on u, they have the same distribution. Because we're dealing with binary data, again, this is equivalent to taking this conditional expectation of the counterfactual y given u are the same. So this is the latent variable formulation of stochastic exclusion, and we can easily see that this implies the previous stochastic exclusion by integrating out u, right? The conditional mean the same implies the marginal means are the same. The second assumption that you can also read off from the SWIG is the latent variable marginal exogeneity. In this case, that is the instrument Z being marginally independent of U, and this counterfactual Y given U is separated from both the instrument Z and the counterfactual XZ. And these two latent variable, what I call the latent variable marginal exogeneity, would imply the previous marginal exogeneity, again, by integrating out U. Or you can read off from the graph, indeed, Z marginally is independent of this counterfactual Y of XZ. Okay. So basically, I'm going to replace the previous two assumptions by these latent variable versions of the assumptions. And these latent variable version assumptions, if you integrate out U, that just recover the previous stochastic exclusion and the marginal exogeneity. Now, the main claim of this talk is to say that actually, if you switch to those latent variable formulation of the stochastic exclusion and marginal exogeneity, you can obtain the stronger Balke-Pearl bounds, and they are actually sharp under those latent variable formulations. Okay, so first, let's see that it's relatively easy to see. If the Balke-Pearl bounds hold on these assumptions, they must be sharp. Well, how do you see that? Basically, we can go back to the strongest assumption of the individual level exclusion and the joint exogeneity. In that model, I can instantiate this model by choosing a particular U. I can choose U to be the set of counterfactual Y, Z. There are four of them. I choose U to be the vector of those counterfactuals. Then the latent variable stochastic exclusion reduces to individual level exclusion, and the latent variable marginal exogeneity reduces to the joint exogeneity. Because we know the Balke-Pearl bounds can be achieved by some distribution under these two strong assumptions, then it follows that just by choosing U in a particular way, if the Balke-Pearl bounds hold, then they must be sharp, and because they can be achieved by choosing such U. Is that clear? Okay. In fact, we have basically seen that in terms of models, and this is a relation. Basically, the latent variable formulation is sandwiched between the stronger hypothesis, the set of stronger assumptions, and the set of weaker assumptions. Okay, just remind you, these are different assumptions, and the latent variable formulation are supposed to be in the middle way between the stronger individual unfalsifiable assumptions and the weaker falsifiable assumptions. It's nothing, just involve conditioning on this latent variable U. There exists such a U, and conditioned on that such U, and you have this reformulation of stochastic exclusion and marginal exogeneity. Okay. Now, I'm going to show then how we can derive the Balke-Pearl bounds under those latent variable formulations of the assumptions. So basically, we have already seen that if you marginalize out the latent variable U from these latent variable formulations, you get nothing but the previous stochastic exclusion and the marginal exogeneity. And we know under those cases, the tightest bounds we can get is the Manski-Robins bound, right? So there must be something that we haven't fully exploited in terms of the latent variable hypothesis. And that is precisely where we have to look at this graph. Okay, so if we look at this graph, this is the SWIG. And basically, we have to move the limbs of this graph slightly in this way. So I'm just doing nothing other than just moving some of the parts in a more apparent way. Then this resembles this famous graph pertaining to the CHSH inequality, where Alice and Bob share a common random source, and they independently get their settings and do their measurements. And the CHSH inequality categorizes this correlation between Alice's measurements and Bob's measurements. So the correspondence would be here, this latent confounding between X and Y would replace the random source, and this little x and little z would replace the kind of the exogenous Alice's setting and Bob's setting, and this x of z and y of xz, these two counterfactuals would replace Alice's outcome and Bob's outcome. Right? So this is nothing but just a realization that the graph contains a subgraph, basically, that should encode this CHSH inequality. Right. So as I said, the CHSH inequality usually or commonly is postulated in terms of correlations. So you have this, so A and A prime corresponds to Alice's measurements when A, so Alice has two types of settings. So A and A prime corresponds to Alice's measurements when Alice chooses one setting versus the other, and the same for B and B prime. And this is the correlations that basically, has 3 plus and 1 minus. That's the structure. Okay, so for our purpose, so basically the secret sauce must be the CHSH inequality, and somehow we'll have to use this correlation encoded by CHSH. For that purpose, I'm going to write the CHSH inequality slightly differently to suit our purpose. So here's a claim. So under the latent variable hypotheses, we have the following Bell CHSH inequalities. So if you look at this, so this is basically, so there are 4 terms, a linear combination of 4 terms, and they have a lower bound 0 and upper bound 1. And uncannily, they have 3 pluses and 1 minus. Okay, so that's like the CHSH structure. And each of the term is actually a conditional distribution of x and a y of xc, but I would advise you to think about this x as the counterfactual x by consistency, right? So this, when z is equal to little z, you can replace this, mentally replace this x by x of little z. So that basically, this is the counterfactual, the joint distribution of the counterfactuals for the arm where big Z equal to little z. And these, the first 2 terms about the counterfactual condition distribution within the z, and the next 2 terms about the counterfactual disjoint distribution with the other z's. So this basically inequality that's relating the 2 different branches when z take the opposite values. This is a relation about the conditional distribution of the counterfactuals conditional on z, but relating to different values of z. Okay. So how did we get this? Basically, we can think about this constraint as the marginalization of these constraints. I'm doing nothing other than just inserting u into each of the conditionals. Okay, so if we can prove this, then by just integrating out u with respect to any marginal distribution of u, I should recover the CHSH inequality. And okay, so let's just look at this sum of this combination of 4 terms. For example, let's just take out the first term. So this concerns x and y's counterfactual distribution given z and given this latent confounder u between x and y. Now, by consistency, I can replace this x by x of z of that particular z we conditioned on. The first step just follows by consistency. And the second step where we have to use our hypothesis. So I'm going to use the latent variable exogeneity. So basically, conditioned on z and u, this x counterfactual and a y counterfactual would be conditionally independent. So I would have x given x, z, and u, and the other term would be y given z and u, but y given u is further independent of z, so I can replace the second one by y given u. Okay, so following this logic, I can basically write each of the term as a product of two terms of this type. And funny enough, what actually comes to bound these sum of four products is actually a really basic equality. So if you you can basically identify these terms as A, B, U, V, and these are probabilities. So they have to be between 0, 1. And for any four numbers between 0, 1, actually, this is a kind of a trivial bound. I want to say it's trivial, but this is quite elementary bound. And this is a bound that you can realize just by looking at the graph of a hyperbolic parabola that 0 is a saddle point. They go down in one direction, they go up in the other direction. Just by using the graph of a hyperbolic parabola, you can basically prove a bound on these combinations of four products. And further, by integrating out U, we get the CHSH inequality as stated here. Okay. So finally, I'm just going to show that if we use those CHSH inequalities, we can indeed derive the Balke-Pearl bounds, because previously we said if Balke-Pearl bounds are true, they must be sharp. Then this would prove that the Balke-Pearl bounds hold under those variable formulations, and they are indeed sharp. Okay, so I'm less technically adequate than Ismail in dealing with algebra. So I think what I'm going to do is doing it in a quite mechanistic way by using linear programs. So I'm going to just set up a linear program. So one set of variables I want to put in my linear program is these conditional distributions of the counterfactual of xc and y of xc. So I can set up these things. These are just conditional probability tables. I can introduce the entries of those variables as programming variables. And then I'm going to encode our counterfactual assumptions. So just think about this guy, this polytope, at the set of counterfactual distributions under our assumptions. So obviously, because there are probability tables, they have to be non-negative sum to 1. So these are simplest constraints I can put in there. And the latent variable assumptions, when I integrate out U, they just become the stochastic exclusion and margin exogeneity. And I can encode them as constraints with respect to those variables. And those are just, affine constraints of those variables. And finally, I will put the previous CHSH inequality concerning those variables also. So in the second step, I'm going to introduce another conditional probability table encoding the observed distribution. So this is just, x and y being binary, conditional z being binary. I introduce those as programming variables, and those are related to the previous encoded counterfactual variables through consistency. So consistency is also, so given counterfactual ones, you can construct the distribution of the observed one. This is nothing but consistency, and consistency is also an affine constraint between these conditional probability tables and these observed conditional probability tables. And finally, because I care about the average treatment effect, although this in principle works for any counterfactual functional that you could care about, I'm going to introduce a variable directly encodes the average treatment effect. And this is a deterministic function that you can compute from the counterfactual conditional probability tables. And then I basically have defined a degenerate convex polytope over those conditional probability tables and this average treatment effect. And finally, I'm just going to use, computer algebra to ask the computer to do a Fourier-Moskine elimination that basically only retains coordinates of the observed distribution, conditional probability tables, and this average treatment effect. Okay, I'm going to do a projection of the convex polytope onto those observed coordinates and the functional I care about. So if we do this calculation, we get a polytope with two supporting hyperplanes and 28 half spaces. And among the 28 half spaces, there are exactly 16 half spaces that has a non-zero coefficient that involves this average treatment effect. And if you look at this table and scrutinize it, you realize these are exactly the Balke-Pearl bounds, because I have the maximum over 8 linear functions in the lower bound and a minimum over 8 linear functions in the upper bound. So these 16 make up exactly the Balke-Pearl bounds. And to verify my claim that the CHSH is exactly the gap, fills exactly the gap between the Balke-Pearl and the Robins-Manski, I can delete those CHSH inequalities, just delete them, and rerun this analysis. And you will find that this table shrinks to half, and those exactly becomes the Robins-Manski bound. So this shows CHSH inequalities is exactly, bridges exactly the gap. So a little bit, I guess I'm running a bit early, but here are the summaries. The CHSH inequality fills this gap. And I want to mention that this is perhaps not the first result that proves the Balke-Pearl bounds using Latent variable. Phil David has a previous paper that he considers a particular Latent variable formulation that avoids using counterfactuals, where he shows the Balke-Pearl bounds hold and they're tight. But I guess this is more explicit in showing the role of CHSH in this gap between the weaker IV bounds and the stronger IV bounds. I think more generally, this kind of points to the message that obtaining tight partial identification bounds perhaps need not rely on unfalsifiable or crossword assumptions. And I would say perhaps looking at the population level swig could be a good starting point in reading off some of the single world natural assumptions when you try to start working on partial identification. And another point, which is the takeaway message, is that to obtain really sharp bounds, we have to think about the Latent variable formulation and to truly understand what the inequality constraints are there in a Latent variable formulation. Again, I think this is where you want to use a graph that encodes both observed and counterfactual variables. And swig can be useful here. So in our case, we consult a swig and we find this particular motive that encodes the CHS inequality that allows us to fill this gap. More generally, I think this could be a strategy to think about swig when deriving those partial identification bounds. And finally, linear or convex, more generally convex programming is a useful tool if you're not extremely dexterous with algebraic manipulations. I want to say, to add to the last point, that this programming can be useful, can be even extended for conducting statistical inference. So for example, let's say I want to actually do statistical inference on the average treatment effect or any counterfactual functional that I care about using data, okay? So this graph, so this green dot here is the actual MLE of the data, consider everything being discrete. And this convex programming actually provides a strategy of doing often difficult inference on those average treatment effects given data. And the idea is that you can think about data, you can think about constructing a confidence region for your observed distribution based on the data. And this gives you this intersection between the observed model and the little ellipses around the observed MLE. And then you can map those back to the counterfactual world and then read off the lower and upper bound for a particular counterfactual functional. And that, if the confidence region has good coverage property, that just translates to the probability coverage property of the counterfactual function. So the idea is, again, represent the counterfactual distribution, observed distribution as probability tables, and encode the counterfactual constraints as linear constraints on the conditional probability table, and link them through consistency. And finally, the added step is to relate the observed distribution to the data through some, convex confidence region around the estimate of the data. And finally, you just query the minimum and maximum in this convex optimization problem. And it would be desirable to use a confidence region that is based on a convex functional of the observer distribution. And one choice could be using a new development of the KO divergence that delivers the finite sample guarantee. Okay, I guess that's all for my talk. Thanks for attention.
Thanks, it's a really interesting talk. So presumably you could have not put the CHSH in directly, but just had a kind of latent variable formulation for the SWIG. Could you, so because you get the CHSH using linear programming as well.
Yes.
So you just have to have types for the counterfactuals.
But are you proposing encoding the latent?
No, I'm just trying to understand whether that's correct, right? So is it just the case that I could not have the CHSH in the program and just say, okay, I know that you know, the latent variable u can, without loss of generality, just contain x of z, and then plug those constraints in, so they're all equalities, and then get the CHSH as well. Does that not
That's
work?
interesting. I'm not sure actually. I haven't tried it.
Yeah, so could you just go back to slide 11, because there's just one thing. So I think part of the, if I'm understanding the logic here, the idea is that we have these, there's a difference between the latent variable assumptions and the other ones that are here, in the sense that the latent variable is postulating the existence of this u. And so, for example, so these bounds were originally derived using potential outcomes. And then there was the challenge for, was it really necessary to have potential outcomes or counterfactuals in order to derive these bounds? And so Phil David then did derive the bounds, but he derived the bounds using in a model where he assumed the existence of a u. But given that the original reason for trying to get rid of the potential outcomes was sort of a philosophical concern that we're not sure that these potential outcomes are well defined, it could be seen as question begging to then invoke the existence of a u, because especially if you read the proof in detail, the u that the proof attains the bounds by considering extremal u's, and those u's are very close, similar to potential outcomes. They're sort of basically the u-take states that make x of z and y of x the deterministic functions of the other variables. So that left open a gap here, which was essentially to say, if we want, can we get to derive the Balke-Pearl bounds without making assumptions about unobservables? Okay, so that's sort of, I think, partly. So it was a sort of theoretical question about what was it? Was there a way to state, if I don't talk about u, is there a way to state what are the additional assumptions that are necessary?
Explicitly u.
But yeah, that's the point. But basically, yes, I mean that's the point of the talk.
Why it's a different thing to assume u is just telling x and z say what to do. Why is that different?
I mean, the issue is to show that these assumptions, the assumptions that are there, the marginal assumptions plus the CHSH got the Balke-Pearl bounds. Explicitly derived that. But there's one other point I wanted to make a sort of comment on this, which is when you're saying random assignment is implausible, I think you mean in the context of an observational study. Because I mean, there are circumstances. Yeah. You can make random assignment here hold by design.
Yes.
In which case it's not implausible.
Yeah,
at least not in non-quantum context. Basically.
I think I'm asking sort of along the same lines. when you invoke sort of a swig and you're deriving inference without invoking cross-world assumptions, if everything's sort of single world assumptions,
Right.
to my mind as a physicist, you're doing something that doesn't involve looking at both counterfactuals simultaneously, such as asking what would y be at the same time for both values of x. And that's sort of like we're limiting ourselves to quantum safe or the kind of logic that works in generalized probabilistic theories. And so you can go to the Bell graph and you can say that the counterfactuals and the instrumental variable can be related to quantities in the Bell graph. But the only knowledge you could then use on the Bell graph to pull back are the sort of same safe assumptions which do not involve cross-world counterfactuals. And CHSH very much is not of that flavor. So the idea of like, oh, you get strong bounds if you make these sort of natural assumptions, the Manski Robins, that sounds fine because that's what you would get if you assumed things which hold for all physical theories and not involving cross-world counterfactuals. And if you make the assumption that cross-world counterfactuals exist, you get stronger bounds for Balke-Pearl. And of course, if you use CHSH, you get the stronger ones because CHSH is entirely based on the existence of cross-world counterfactuals. That's like the premise behind it.
Yes,
So it's just
yeah, that's exactly the point.
Okay.
I feel like, yeah. I mean, yeah, you basically need some type of cross-world assumption, but in this case, that's induced by the very existence of this Latent variable u. So I guess that's sort of what I would say. Because you just look at this formulation itself, it doesn't seem to involve cross-world statements, but once you uncover this underlying CHSH, it's actually, it is a statement involve different, cross-world correlations. And you have to use this to arrive at stronger bounds.
Thank you. But I think to follow up, my point is, when you condition on this unobservable u that is not really defined, this u could also contain y0. So in some sense, you may make some cross-world assumption, right?
Yes, it may or may not. I remain agnostic about the nature of u.
But really, because you are agnostic about that, that's why I think that maybe the situation that is giving you this bound is a situation where the u is exactly related to y0, and then you are making some cross-world assumption between y1 and y0. That makes sense what I am saying? Or?
So you're saying that at a point where the bound is achieved is where the u is instantiated by y0.
Yes, it's a function of like y1 and y0. So yes, so that's why I think I want to get more sense about what are the algebraic situations that gonna give you the estimal point, because those estimal point could be exactly the situation where u is a deterministic function of y1 and y0. That's why you are getting this CHSH. I think this is just my intuition.
I don't know, it's possible. For example, if you look at the, for example, Balke-Pearl bounds can be derived when you instantiate u to be the set of 4, the vector of counterfactuals. But is that the only case? I don't know.
Just to add a quick comment here. I mean, basically, part of the language was, supposing I'm someone interested in the Balke-Pearl bounds, but I don't think in terms of use. And the only quantities I've got are x of z and y of xz. And then I'm willing to make those weak assumptions. And then I want to understand what extra would I have to make in order to get to the Balke-Pearl bounds. And I understand that, this is probably not surprising to people in here that CHSH inequalities are, intimately tied to the idea of there existing as latent variable. But for example, if you read Pearl's work, then he talks about testing the IV inequalities as being like the Bell inequalities. So it's about the falsification test and the instrumental inequality. So it wasn't totally obvious to us, at least when we started out, maybe sort of simpler for people think about Bell's inequality for longer. It wasn't obvious to us that that was the missing piece and that was all that was needed. That was the only piece that was needed that had to be added. So it's not that we're advocating assuming the CHSH inequality. It's just that we wanted to understand in a language where you don't talk about u, you only talk about y of xz and x of z, what is the extra piece that you need to get from these very weak assumptions to the Balke-Pearl bounds? And that's the question that we're answering.
Yeah, thanks. Let's thank the speaker again. Very brief break and I'll come back 11:30.